And we're going to do a quick video for you on preconsolidation pressure using the virgin compression curve. Okay, so we have the virgin compression curve here. Don't worry if you don't know what that is right away, I'll give you a quick explanation. And we're asked to find the preconsolidation pressure, sigma c. Okay, so I know in some books in geotechnical engineering, the notation is different for a lot of these questions, especially when you do foundations engineering. Like there's like 4 different formulas for everything. So we're using sigma c here for the preconsolidation pressure. But you know, in some books it might be sigma p. Ask your professor, make sure. Okay, so it's good before we start to have a slight understanding of what consolidation is. So consolidation happens in clays, very fine-grained soils, not granular soils like sand. Okay, in which the clay, after it's loaded, okay, the water within the saturated clay cannot leave immediately. Okay, and because it can't leave immediately, a pore water pressure is increased as a result of that, and then slowly over time, the clay will drain into nearby sand layers, and that drainage over time causes a settlement. So yeah, essentially that is what consolidation is it's a gradual increase in the effective stress of the clay layer, and it causes settlement over a period of time. I just kind of drew a little diagram down here for you. What that exactly looks like, okay, is you have a loading. For example, you could build like a foundation, a concrete foundation, and on top of, right below it, you may have a sand. Here's our water table here. So we have a saturated clay layer, okay, that's being exposed to some stress as a result of external loading. Okay, and the water is slowly being squeezed out of that clay layer and it's draining into the sand layer essentially. And as a result, the effective stress in the clay layer is gradually increasing. So let's take a look at this virgin compression curve. So what does this curve mean? Well, so at the end of consolidation, so you'll probably in your labs in geotechnical engineering, you'll do the consolidation test. Essentially, what it is, it's a period of 24 hours. You're periodically taking settlement readings over time, and you're slowly increasing the load in order to kind of have an exaggerated idea of what the consolidation would look like on a clay sample. At the end of the consolidation, this is what the void ratio relationship to the log of the stress, or the vertical effective stress. This is a semi-logarithmic graph because, as you can see, in the y-axis we don't have a log value, and in the x-axis we do have a log value of the vertical effective stress. You may also see it written as log p. Okay, we're using log sigma right now. So essentially what's happening here, okay, as we're loading and near the end of the loading, what's going to happen, all right, is as we can see, the void ratio is decreasing, okay, and as we get to the unloading phase, this is called the rebound curve, and as we unload slowly, we measure that unloading and how it affects the void ratio and the effective stress relationship. Okay, so with that being said, okay, and actually this is sigma prime, we'll say, so it's the effective stress. How do we find the preconsolidation pressure? Okay, so it's actually a graphical method, and it's called the Casagrande method. And how we're going to solve that is pretty simple. So you'll probably be given this, and I'll show you the steps. So there's 5 steps. The first thing is that we're going to do is we're going to find by eye what you think to be the sharpest curvature of this portion of the curve. Okay, so I think it looks to be about here. Okay, so whatever you think has the sharpest curvature, okay, is so essentially the smallest radius of curvature. Okay, that is what you're going to select as your point O. Okay, so we're going to select that as point O, and what we're going to do is we're going to draw a horizontal line. Okay, so we're going to draw a horizontal line. Okay, we can call it OA. Okay, call that line OA. Next step, we're going to draw a tangent line. Okay, that is tangent to the curve at point O. So at point O, we're going to draw a tangent, okay, to this curve here that intersects point O. Okay, so that's going to be referred to as our OB line. Okay, and next what we're going to do, okay, is we're going to draw line OC, and line OC bisects line OA and line OB. So we just draw it. What that means is we're going to draw a line as best as we can. If you want to use a protractor just to make it perfect, that's good too. Okay, so we're going to draw a line that bisects, so that's in the middle of AB. I know that's not exactly perfect, but just try and make it as good as you can. A lot of the times they just want to see that you know how to do this, okay? So where this is going to be OC. Okay, so the next step, the straight line portion of this curve here, this straightens out, so this is straight, and we call that actually C sub C, so the coefficient of consolidation. And what we're going to do is we're just going to extend that line where the straight portion is, and we're just going to extend it straight up like this. Okay, and where we extend that line, okay, and where it intersects line OC, Okay, we drop a line down to the log effective stress axis. Okay, and where that intersects the x-axis, okay, is the pre-consolidation pressure sigma prime c. Okay. All right, so there you go. One thing to note is actually the value of this. We can determine whether or not the soil is normally consolidated or over consolidated or pre-consolidated. So that's for another video though. That's how to find the pre-consolidation pressure.